advantages of attending lessons. Okay. Yeah. So maths and physics. So for me, I'm going to try, as I said last time, I'm going to try to explain the math because we'll be using math to explain the physics. Okay. So the most important, the first thing, then if there's a hand, if you've got a question, just ask. Okay. Most of the times, I won't even see your hands. Si vous avez des questions, s'il vous plaît, just open your mic and ask. Okay. This is a good number. All right. So when you want to express the vector, the position vector OM, what you need to have is the magnitude or the size of OM, or the distance between OM, which is, for example, R. Okay. Then you also need the unit vector. Okay. This vector is incomplete. You are just using the magnitude. So you also need the unit vector in this direction. Okay. Unit vectors are there to show us the direction that that vector is taking. So whenever you're writing any vector, you have to identify the unit vector in that direction, and you also have to identify the magnitude. That's all. Okay. Then a unit vector is, we define the unit vector to be that vector divided by its magnitude. Okay. For example, we know that OM can be written as R, magnitude R, in the direction of UR. We said the unit vector is there to show us the direction. So what is OM? What is the magnitude of OM? For the people who didn't join us or never watched the video, this is how we present the magnitude of a vector. So this mathematical tool will extract the magnitude of OM. Okay, so which is R. So when you cancel, which we're going to have the unit vector UR. This is why this formula is true for as a formula for the unit vector. So the unit vector is always, you get that vector, you divide by its magnitude. That's what you need to know. And the unit vector, we use it to denote direction. So the unit vector, this vector has to be a unit vector or of magnitude 1, so that the overall magnitude of RUOM is just R, as denoted in the diagram OM magnitude R. Okay, so if I pass on the unit, the magnitude formula, if I pass on, so I will say what is the magnitude of R, and I also say the magnitude of UR. Okay, so what is the magnitude of R? That's magnitude of UR times 1. So this is going to be R. This is why the unit vector is just there to denote direction. Then last time we also talked about the special unit vectors. Okay, so you have the Cartesian coordinate system. Watch the coordinate system, s'il vous plaît. Watch the coordinate system Z, and then you define a unit vector in the direction of X. Of course, its usually is small because its magnitude is 1. So this unit vector is called G. This unit vector is called E. Most of the time it's called E. Then this unit vector is called K. Okay. So E, G, and K are unit vectors. This one in the direction of X, this one in the direction of Y, and this one in the direction of Z. Okay. So for E can be written as 1 because that's good magnitude and direction, plus then everything else will be 0 if you want to decompose it into other components. Then I also taught you that a unit vector, you also write it as a matrix. You can also write it as a matrix. So when you write a vector as a matrix, forget about the direction. Okay, so you just get magnitude. So here you're going to get 1, then here you're going to get 0, here you're going to get 0. So E is written as 1, 0, 0. So this shows that this is in the direction of E, this is in the direction of G, and this is in the direction of K. So it's the magnitude is 0, 0, then it's only 1, in the direction of itself E. Okay, so you're not supposed to show this. Chodo, am I audible and can you see everything? People are quiet.
Yes, you're audible. You can see everything.
Okay, shock and be so if you don't if you don't want to, if you're using the base system E, G, and K, these are unit vectors that are used to show direction. The unit vectors are just there to show the direction. Okay, so for example, let's say a point in M, the coordinate system, another reason to watch the coordinate system, then this is point O. So for you to locate point OM, you're going to, it's just going to be simple. Point OM is, you're going to say, since you don't know the exact magnitude in the x direction, you just say x, but you saw the direction in the direction of E plus y in the direction of G plus z in the direction of K. Z is in the direction of K. Then, if you don't want to show these unit vectors, you always leave it as a matrix. So this will be x, y, and z. Then a special case is when we have OM is equals to E, the unit vector E, then which can be written as 1, but you don't show 1, so just say E plus 0 G plus 0 K. So if you want to leave out the unit vectors, you just get the magnitudes 1, 0, 0, 1. I had the question, someone was asking me where I was getting this. So same applies to G. G is written as 0 E plus 1 G plus 0 K. Okay, so as a matrix, you just get the magnitudes. So this is how you write G. Then K. I'm being a bit fast because 0E plus, this is what we did last time, 0G plus 1K, as simple as that. Then as a matrix, then we always use matrices when we're doing calculations. Okay, 0, 0, 1. Okay, then so with your homeworks, I'll be addressing certain issues. There are certain issues that I've seen in your homeworks. For example, these three vectors E, G, K, as you've seen, they are unit vectors. These unit vectors are perpendicular to each other. So this is G, this is E, and this is K. They are perpendicular to each other. And we also learned about the product. So you can watch my video if you didn't watch it. We learned about the vector product. We said if you get the vector product of E vectorial G, what are you going to have? You're going to have a vector such that that vector is perpendicular to both E and G. So here, from this diagram, the vector that is perpendicular to both E and G is K. So you're going to have K. So now I showed you that you can demonstrate this using. We also learned how to um, how to evaluate vector product. You can watch my previous lesson if you are lost. So then one of the examples, each people haven't submitted the homework. Okay, but from the homework, okay, I'll just give an example. For example, E which is written as, whenever you're doing calculations, you use matrices. You write a vector as a matrix. So you say 1, 0, 0, vector A, 0, 1, 0. Okay, so you carry out the vector product. So the vector product of E and G, I'm not going to carry out the vector product because I showed you last time, but it's going to give us, when you carry out the vector product, it's going to give you E, which is equal to K. Okay, now I was seeing some people, they were getting 0, 0, everything 0, 0, maybe when they carry out a certain vector product, which is true, they'll get 0, 0, 0. This means that now they were putting this. I was failing to understand what they meant, because this is not K. 0, 0, 0 is not K, but why, and what does this mean? They were putting this, and a lot of people have submitted were showing me this. I don't know if You are just texting your friend, send me the homework. Because why do you have the same thing and what does this mean? This doesn't have songs. This doesn't have meaning. This is not car. If you want to say this is car, this is not car. S'il vous plaît. Because I've showed you how car is written. Car has to be a unit vector of 1 in the z direction. I don't know if they were trying to show me that 0 is in the direction of E. The other 0 is... Because if I write this vector, this is a 0 vector. Okay, oh, what's that? So this is a 0 vector. So if I write this vector, let's say this vector 0, 0, 0 is simply written as 0e plus 0g plus 0k. So this is a 0 vector. It's 0, it's 0 in all components. So this is a 0 vector. We put an arrow to show that it's a vector on top of 0. So I don't know. I don't know where I wasn't understanding what was going on with when they say 0, 0 and they put a arrow. No, once wachabika arrow imweni, then wabisabika ka. The homework is for you to practice. Then I'll see you only see your mistakes if you're practicing. Okay, so I will see. Okay, I will say okay, like I've seen now. Okay, people are finding this mistake. Okay, so I will talk about it. Okay, let's get on. So we're now 16. Some people haven't joined. Yeah. So I don't know if you've got questions so far. Chora, is everything okay in terms of visibility? The three mathematical tools that you're going to use. Last session I explained what they mean, but now we're going to look at them mathematically, like how to evaluate gradient. Okay, gradient of a scalar function, how to, then in three coordinate system, that is you have another reason to watch the coordinate systems, the Cartesian coordinate system. You also have the cylindrical coordinate system. This is iffy. Then K. Then you have the last coordinate system, which is ER, E theta, then EPhi, which is the spherical coordinate system. So you find gradient to be different depending on the coordinate system that you are using. Same with the divergence of a vector. Then same with the rotationnel of a vector. Okay, so we're going to start with gradient. So we defined the gradient as the steepness. You're finding maybe after a certain point. If you've got a function, you don't what differentiation comes from. If you've got a function, then maybe at this point you want to know whether the function is going in this direction, or maybe how steep that at this point how steep it is. Okay, and in which direction it's going after this point, maybe this point A. That's what gradient does basically to a function. So now then with gradient you have a function which is a scalar. These are the most important things to know. So a gradient, if you've seen there's an arrow on top, which means gradient is a what? Is a vector. That is, it has got magnitude, okay, and direction. So what does this mean? Plus direction. So what does this mean? The expression of gradient, for example, will have, maybe for example, let's say we have a magnitude and a direction attached to it, because it's a vector. Then what else do you need to know? So gradient converts a scalar into a vector. Then divisions converts a vector, as you've seen here, into a scalar. So if you've seen on divisions, there's no arrow for the whole thing. So this will be initially this will be a vector which will be converted to a scalar. This is a scalar, doesn't have direction. So this one won't have unit vectors that show direction. Then rotationel converts a vector into another vector. Okay, then I explained in another that session, I said that divisions is just you quantifying the how much that vector is converging or diverging. Okay, for example, one of the vectors that you'll be working with is the electric field vector. So the electric field vector for a positive charge is represented as outward uh, diverging. Therefore, the divisions, which is the scalar of the vector E, will be non-zero. Okay. Then the rotation of E, I explained that rotation shows us how much the vector is, how much it's like you're quantifying the rotation. So mathematically we say the rotation of E. So rotation of E is equal to 0 because this vector is either diverging or converging, the electric field vector. Okay, but when you start looking at another component of this module, we'll also learn about the magnetic field. So the rotation of a magnetic field, which is magnetic field, which is represented by B, will be non-zero because you will learn that the magnetic field is rotating when you draw it. So that's it. Those are the applications of gradient, divisions, and rotation. Then we also learned that the rotation of gradient, gradient of anything is 0. Why? Because the gradient of anything is just maybe, for example, a slope. So maybe gradient of f, this is gradient of f, which is a vector. So this vector is not, the question that you only need to ask yourself, is this vector rotating? If this vector is not rotating, this vector is going this way, it's not rotating, obviously. So its rotation is equal to gradient of anything is 0. This is an important mathematical equation in physics. You're going to use it a lot. Okay, you're going to use it a lot. Okay, so for you to understand these equations, for me, my job is to make you understand these equations, because even when you start your school, they're not going to explain to you. I was never explained understanding what rotation is, even just telling me that it's a vector. For us to have a rotation of something, a vector has to be rotating. Or for us to have divisions, they will never explain to you in this way. They will just be giving you these formulas. So take this opportunity to learn something such that when you have this module, you will remember, you'll be connecting because you have a lot of formulas already. For example, I've got this equation, you have a lot of equations, but all those equations, you can actually understand them instead of memorizing them. Okay? All right. Yeah. So now that's the physics part of gradient, divisions, and the rotational. Now let us look at the mathematics part. So how do you quantify gradient? Okay, from the Shan, you've seen one example for the homework. If I told you are solving your homeworks on your own, you've seen that I asked you to find the gradient. So gradient, uh, for you to know these three operators, mathematical tools, you have to know the operator called nabla. And I defined nabla to be. I also told you to look at the partial derivatives. They will be very helpful. Okay, how you should know how to find the partial derivatives of a function that you can check on YouTube if you don't really understand. But I try to explain as well. Okay, but that's just like below the scope of our course. So, Ado, the nabla. You will see why this I'm emphasizing on nabla. So nabla in Cartesian coordinate system, nabla differs depending on the coordinate system. So nabla in Cartesian coordinate system, that is when we say Cartesian coordinate system, think of this coordinate system. You should also watch the coordinate system, s'il vous plaît, y, x. Okay. So nabla in Cartesian coordinate system is none other than okay. So nabla is none other than you you write it, if you want to write it as a matrix, because you'll be doing calculations with nabla, so it's better you write it as a matrix. So you say the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z. So you can now convert this into a normal vector. You can also write, these are magnitudes, the partial derivative with respect to x, in which direction this is in the e direction. When I write this, it's just to show you that this is in the e direction. I don't mean when you write vectors you shouldn't include this. That's not what I mean. No, I'm just showing you. Okay, then plus, so this is in the direction of g or y. Then these are unit vectors, plus z over del z, the direction of k. That's nabla. When you, this is nabla in the Cartesian coordinate system. Why in the Cartesian coordinate system? Because it has got t, e, g, and k. E, g, k are the base system of the Cartesian coordinate system. So they can ask you, so you find the gradient of a function depending on the coordinate system that you are working with. Okay, then the question is, why should we trouble ourselves trying to calculate the gradient if you're calculating the same thing, gradient of a function in different coordinate systems? The answer is simple. The more the other coordinate systems, the calculations will be simple. Uh, it will be easier to calculate the gradient of a function if you use, for example, the cylindrical coordinate systems or the spherical coordinate systems. I'll give you an example that proves what I'm from telling you. Okay. Then, so this is nabla in the Cartesian coordinate system. You have to know nabla at all cost. Then nabla in the cylindrical coordinate system. Cylindrical. So meaning the equation of the gradient depends on the coordinate systems. Please watch the coordinate systems. I've seen, you will learn more about coordinate systems with Mécanique du poids. Okay, inshallah. So nabla in the cylindrical coordinate system is, so how do I know this formula? I start with identifying the unit vectors in the cylindrical coordinate system. The unit vectors are e rho, e phi, then ez or k. Okay, ez. Then, so the first element is e rho, right? And rho is the radius. Okay, so here we have the partial derivative with respect to rho, sorry. Okay, because the first part is e rho, and rho, if you look at the coordinate system, you find that it's a radius associated with e rho. Then the second component, you look at the second component here is e phi. Okay, phi, whenever you find partial derivatives, phi is the angle, so you convert that phi. So when you watch or when you look at the coordinate systems, you find that rho is associated with phi. Okay, so whenever, so we will not deal with the angle, we'll deal with this arc length. And for people who did ADMA, but don't worry, if you want to find this arc length, you just simply multiply the radius multiplied by the angle. That's the arc length. So arc length is radius multiplied by the angle. Why is this information important? Whenever you're writing an expression of nabla in the cylindrical coordinate system, the first step is you identify, you have to know the coordinate systems that are the base. For example, in the cylindrical coordinate system, you knew that I have E, G, and K. Okay. For the spherical coordinate system, we use E rho, E phi, and EZ. So the first question that you ask for the first component, it will be E rho. So you just do the partial derivative with respect to E rho. Okay. Then you are not forced to find arc length because rho is the radius. Okay. Then E rho is in the direction of rho, the unit vector. Okay. So the first component will be in the direction of E rho. Then it's just because this is already the radius is like the distance or the displacement, the distance. So you just say with respect to rho. But here's the trick. When you come to Ephi is the angle. The coordinate systems, Ephi is the angle. Phi is the angle. Therefore, you say the partial derivative with respect to phi, of course. Then you multiply this del. This is what we call this del. When you multiply this is like a smaller change, maybe the angle, smaller change in the angle. When you multiply rho multiplied by angle, this is a smaller change in angle. This is arc length. So since this was distance, this rho has to be converted to distance just by multiplying rho. In other words, you just identify phi is associated with which angle, rho, radius, rho. So you put rho, then phi. Okay. Then the third component is Ez or K. This is when you watch the coordinate system. This is in the direction of Z. So what you do? It's Z then over Z. You don't change anything. It's the same. It's the same as here over Z because it is. I said the cylindrical coordinate system borrows the last unit vector. They borrow it from Z. So this is the same as K. So K is associated with Z. So this is in the direction of Phi, the unit vector Phi. Then this is in the direction of the unit vector Ez because or K, depending on the notation that the book is using. So, ladies and gentlemen, this is how we find nabla in the cylindrical coordinate system. I know it looks like a lot, but trust me, with the step-by-step method, you find that fairly uncomfortable. So I can also you express nabla as a vector. Okay, nabla is a vector, it has got an arrow. So you say del over del phi. If you want, you can just water this formula for nabla, but there are a lot of formulas. So I'm trying to give you information that will help you even swatter because you can only swatter if you understand. I'm not using any reference. I learned this a long time ago. I'm not using any reference to teach you to give you all this information. It's because I understand. So if you understand, it's even easier for you to sort. So the second component, the second magnitude is rho dead phi. Yeah, just remember that whenever I've got phi, I have to multiply it with rho. Whenever I multiply rho times phi, it's like you're converting that angle into arc length. Because here you had rho is the length. This is also the length. Then in the direction of Fu, of course, then plus del over del Z in the direction of Ez, of course, or K. As simple as that. Then the next question is, don't worry, when you do a lot of exercises, you memorize all these. Don't worry. So now in the spherical coordinate system, so with when you start your school, they'll just give you this. They won't even tell you why nabla is important. I will show you why nabla is important because when you memorize nabla in each coordinate system, it will be easy for you to find the divisions, gradient, and the rotationnel because you'll just be using nabla. So the first thing that you do is the first step by step, right? Identify the coordinate systems of the spherical coordinate system. The unit vectors. It's e theta, then e phi. Okay, that's the first step. So you have to know. according to the coordinate system. So you have to know. Okay. Then you theta and phi are angles. So you have to say what radius is associated with theta r, which radius is associated with phi. The same one there, it's rho, the one that we used in the what. Then r is the radius, of course. So there's no need. Then you just write. You put them as a matrix. So you say the derivative of with respect to the partial derivative with respect to r is already the distance, so there's no need, it's not an angle. But the second element, this is in the direction of er. Then the second element, what's the second element? Theta. Theta is associated to which angle? R. So you just put r down. So you say partial derivative with respect to theta, but since this is an angle, you say r. You identify which one. And then according to different schools, they'll be using different notations. Okay, so when you just have to know like er. Normally it's er, e theta, e phi. Most of the schools you find this, but it can differ. Maybe the theta they'll be using phi, but it's just the same reasoning. So if they're using theta for phi, then you also have to identify what theta moves with according to the notation that you're using from your school. Then the last one is also an angle. Okay, the last one is also an angle. So you say the derivative, partial derivative with respect to that angle, which is phi. Then down here, since this is an angle, you put the radius associated to it. Now the radius associated to phi is rho. Then if you've watched my coordinate system, we found that rho is equals to always equal to sine r sine theta. So we don't use rho in the spherical coordinate system. That's the difference. So here we use the rho, but in the spherical coordinate system we don't use rho. So, but one thing that you have to have in your mind, phi is an angle that moves with rho. So instead of rho here down, you put r sine theta. Okay, therefore your nabla in the coordinate system, in the spherical coordinate system, will be the partial derivative with respect to r of in the direction of er plus the partial derivative with respect to theta. Of course, this is e theta. Then here you say e theta, but this is since this is an angle, you put the radius which is associated to the angle, then plus the partial derivative. Okay, this is e phi. Now, since this is an angle as well, phi is an angle as well, you say dead phi, and then you put rho here, but you just have to know what rho is in the spherical coordinate system because we don't use rho in the spherical coordinate system. So you say r sine theta, which is the equivalence of rho. I explained vividly why rho is equal to r sine theta if you want to know that. But for now, you have to know this. Okay? Now, after expressing nabla in different coordinate system, it's now high time we can find the gradient in each coordinate system. For example, the gradient of a function will be defined as nabla f, no matter the coordinate system. Okay, so nabla is a matrix, 3 by 1 matrix. Okay, then according to the Cartesian coordinate system, it's very simple with respect to x, with respect to y. I've showed you how to construct this with respect to z. Okay, then multiplied by a constant out. According to matrices, when you have a constant out, you just take it to all the components. So you're going to have, therefore, the gradient in the Cartesian coordinate system is del f over del x, del f over del y, then del f over del z. That's it. So you have to find the partial derivative of f with respect to x, the partial derivative of f. This is why you have to know how to find partial derivatives. Now, how about in other coordinate system? You just have to identify what is nabla in the cylindrical coordinate system. They will be specifying, find the gradient in the cylindrical coordinate system. So the formula doesn't change. Gradient of that function is equal to nabla f, which is equal to what? So your only job is to know. Okay, so over me, I know the rho. This is the cylindrical coordinate system. Rho, they use rho. Then here there's an angle phi. So over, who is that one? Dead phi. Then I'll put rho because this is an angle. Then down here it's z because the cylindrical coordinate system borrow from this one. Then I'll multiply by f. So from here, okay, how many minutes? Actually, when we have 3 minutes remaining, s'il vous plaît, laisse-moi savoir, okay?
All
Like,
right, and I just wanted to ask, by the way, if you're recording the video.
yeah, I am recording the video, yeah,
All right.
but it's advisable for people to be in attendance so that they can follow with me, okay?